Okay, so let's look at digital certificates and trust. So along the way, we'll touch base on some aspects of proving identity, but we'll focus mainly on using public keys to be able to identify entities in a digital way. Okay, so what are digital certificates? Well, you might access a web page. Typically you would use HTTPS and then with a URL after it. But there's an important part of this, and there is normally a certificate that supports whether a site is trusted or not. It is this certificate which is used to expose the public key of the website. And as we'll find out, it's this public key which can identify whether the domain that's been connected to is trustworthy or not. And we'll try to understand how that actually happens. Underneath, when we use HTTPS, we typically use a key exchange method. And at the end of that, we will generate the same symmetric key. Often this is AES encryption, and it will be used to encrypt the data between the client and the server. But it is public key encryption which is used to identify whether the site is trustworthy or not. And as we'll find, an important element of this is the issuer of the certificate. Because it's the issuer of it's the trustworthiness of the issuer which will actually define the validity of the public key. So in any authentication system, we need certain aspects. We have authentication, we can have confidentiality, and we can have assurance. And these aspects are important. Authentication makes sure that we're authenticating to a remote service, and also to authenticate a user onto that service. Confidentiality makes sure that our communications are kept secret, and assurance means that we can actually make sure that what we send and receive is actually received correctly by the other side. We might also define CIA, confidentiality, integrity, and availability. Okay, so the problem that we have is, how do we make sure that if we're using public key encryption, if we have Bob and Alice, how can we reliably get Bob's public key over to Alice in a trustworthy way? Because unfortunately, Eve could be in the middle, and it could be Eve that's sending Bob's public key to Alice, and for it not to be the right public key. So when it looks like Bob is signing for something, signing with his identity, then Eve may be sending the wrong public key and then pretend to be Eve. So we need some way to be able to make sure that this key can be sent over to Bob in a trustworthy way. So we'll have a look at how we set up what's called the PKI infrastructure, or the public key infrastructure, to make sure that we have trustworthy public keys. So first, let's look at what we are protecting. Well, obviously we are protecting or authenticating users. We authenticate our devices, our data, and obviously our systems. So each of these entities needs to be authenticated in some way, and we might do this authentication in different ways. So we might authenticate our users with biometrics, handprints, fingerprints, and so on, devices with their MAC address for the network card, and so on. And the two basic principles that we have when we're authenticating is to use either end-to-end authentication or intermediate authentication. So with end-to-end authentication, we go from one end to the other and authenticate one entity to the other. With intermediate authentication, we might have a device here, a network router, and what we do is that we will just do intermediate authentication. So maybe that's the scope of the authentication, where this device authenticates itself to this device. In this way, we can see that other parts of the authentication chain between Bob and Alice aren't authenticated. But in this case, end-to-end authentication allows Bob to authenticate to Alice and vice versa. So the ways that we can do this is to go for one-way authentication. So if we define Bob here and Alice over here, and let's say Alice is a server and Bob is a client. The client connects to the server. With one-way authentication, what happens is that Alice identifies herself to Bob, but Bob doesn't authenticate or prove his identity to Alice. This is the type of system that's used with HTTPS, and where the website authenticates itself to the user, and this is one way. Server authentication. We can also get where Bob authenticates themselves to the server, and this is sometimes used in Wi-Fi systems, such as in EAP TLS, where Bob has some key that he passes to the server to prove himself. It's also used with devices, where devices can prove themselves to some service. So this is one-way client authentication. And then the final way is mutual authentication. And with this, Bob and Alice, or the client and the server, can authenticate each other. And overall, this is likely to be the best if we can do it, but obviously it has an overhead. And PEEP is one example of this that we see in Wi-Fi, where we get mutual authentication. Okay, so that's our authentication methods that we have. And there's multiple ways that we can actually do these things. So for devices, we might use MAC addresses or an IP address, or perhaps a passphrase or encryption key. But for users, we often use a multi-factor authentication method. So if we have users, then we often split this into 3 or more different areas. Something you are, something you know, and something you have. There's another one, and it's somewhere you are, such as your GPS coordinates. And this is used to authenticate a person. So the something you are is typically the biometric methods. So it might be a handprint, because your hand is fairly unique in its layout, the length of the fingers, where the lines are, and so on. So a palm print is quite a good method. We also have iris scanning, fingerprints, and even DNA. An interesting one is the vein pattern within your eye and also within your fingers, because that is fairly unique. When it comes to something that you know, obviously that is our passwords and our general knowledge questions. Something you have can be a network adapter. It could be a digital certificate, and so on. Somewhere you are is possibly your GPS coordinates. In this way, we can authenticate the user by taking 2 or more of these areas. We might ask the user for the password and also use fingerprint recognition. Increasingly, we're using face recognition too as part of this. Okay, so these are some of the ways that we can actually authenticate our users onto a system, and hopefully it becomes more trustworthy. Okay, so what do these digital certificates actually look like? Well, let's look at public key encryption first. So with public key encryption, we have a key pair. And so we have our private key and we have a public key. And we use them together. If I encrypt with the public key, I decrypt with the private key, and vice versa. So when we're proving our identity, Bob will take a hash of the message, and then we'll use his private key to be able to sign the message. So then we get a signature that can go along with the message, and then when Alice receives this, she does her own hash of the message and then checks the signature against the message, But for this, she uses Bob's public key to check the signature. So we need a way to get the public key to Alice in a trustworthy way. This is Alice here. And the way that we do this is with a signed certificate. And these certificates are often known as X509 or a digital certificate. And there's two main formats for them. One which contains both the public key and the private key. And normally there's a password on this to protect it. Because we don't want to leak the private key. But we also have a distributable form that we export that has the public key on it. And this way we take our key pair, so we generate a key pair here, and we would keep it in a certificate, say, and then we export into a certificate which has the public key on it. This public key is typically an RSA public key, or it can be elliptic curve. But RSA is the most popular, and it needs to be at least 2K or 2000 bits, 2048 bits long. Within this we have the details. We have the issuer of the certificate, and I'll explain the issuer in a little minute, but it's very important. We have the public key stored on it, and we also have a thumbprint, and it's this thumbprint which provides a signature for the certificate that has been signed by the issuer, and that will provide the validity of it. Okay, we also have other things like the date, the expiry date of the certificate, and so on. Some of the formats that we might use for our certificates, we have a P7B format, which displays it in a base64 type format, and we'll see something like begin certificate and end certificate with a whole lot of base64 characters in between. This is the text format and allows us to be able to embed our certificate inside an email or in a plain text document. But there are other formats. PFX and P12 are binary formats and support password on these certificates. And it's very important that we protect especially this certificate here, because it can be used to sign for things if someone was to get our private key. Okay, so the basic mechanism is that Bob will hash a value, encrypt that. I'll explain in more detail the mechanism for that later, but we'll create a signature, then he sends in the message in the signature to Alice. Alice will then use Bob's public key to be able to check the signature against the message, and then she'll know that it was Bob who signed it because only he has the private key, and that the message hasn't been changed along the way. So for this, what happens is that Bob will send his public key in a certificate. So this key in here, he sends a certificate to Alice, and Alice will check the validity of the certificate for the issuer and its thumbprint and so on, and will know to trust Bob's public key. Okay. So the commands that we use for this is with OpenSSL we use X509, and this will produce an X509 certificate. And with this, what we can do is that we can import our key. So the PEM format is a typical way that we represent our keys, and then we can output that to a certificate file. So in this way we can actually create our key pair and then create our certificate. So the standards that we have for this is X509 certificate and a DER format. And a DER format is a binary representation of the certificate. The other format that we have is PKSCS number 7. And this represents it in a base64 format. Okay, so those are the two main formats that we have, the binary format representation or the base64 ASCII representation of the certificate. So now let's look at PKI. And with PKI, or the public key infrastructure, we have a hierarchy. And what we have is we have a trusted root, CA, or certificate authority. We then have Bob and Alice, and we'll define the root CA as Trent, a trusted entity. And Trent is trusted to sign for these certificates. So he will take his private key and then sign a certificate for Bob. So let's say that's a certificate, and within that certificate we have Bob's public key, and that will be Bob has requested this, and Trent will sign that certificate with his private key. Bob receives that, and it'll have his key in it, and then can forward that to Alice. Alice will then check the signature on the certificate. So Bob himself will have his own public key, and Alice will have that installed on her computer. So when the certificate comes in, just like we did before, Alice will check the thumbprint or the signature on the certificate and to see if it ties up with Trent's public key. If it does, then she knows that Trent is the one who's issued it. Unfortunately, Eve could trick Trent into pretending to be Bob. And if Trent doesn't check for Bob's identity, then it could be Eve that's sending Bob's public key to Alice. And in this way, Eve could pretend to be Bob. So the trusted root CA should really do a check on Bob's identity to make sure that he's not issuing the certificate to Eve. We get another level from this hierarchy. So we have a root CA. These are top level certificate authorities who can assign any certificates that we want. Below that we have intermediate CAs. And these intermediate CAs can sign for specific things. For example, we might get one that signs for devices. So say on a Windows operating system, we will get a digitally signed verification that the device has been issued by a certain manufacturer. We might have email certificates, and we also have web certificates. So these intermediate CAs can sign for different application areas, and then these intermediate CAs can issue certificates. At the lowest level, we have what's called self-signed certificates, and these really should never be trusted and only used for testing. So a self-signed certificate means that the person who's issuing it is also the person who signed it. So really these should not be trusted, and these days most websites will not accept a self-signed certificate. Okay, so let's talk through the basic steps that we go through in terms of using public key encryption and authentication for Bob and Alice. Okay, so let's first start here. So this is Bob, this is Alice. So we'll talk through the main steps that we'd use to use public key encryption for both the security of the message and also to identify Bob to Alice. Okay, so initially what we would do is that we would have our message, and here it is. Now to send Alice an encrypted message, so we've got Alice's private key, and there's Bob's private key, and we've got public key for both. Now Bob wants to send the message to Alice using public key encryption. Okay, so we're not using symmetric key encryption here, we'll just use public key encryption for both the encryption and also the authentication. So Bob will use Alice's public key to be able to encrypt the message. Okay, before he does that, he will take the message and then create a hash of it. So we're going to create a hash of the message. What happens next is that Bob will use his private key to then encrypt that hash. So we now have an encrypted hash with Bob's private key. Next, he'll take the message and the hash and then encrypt all of that with Alice's private key. When that goes over, so we'll get that over here, and we've got the message in there. And we've also got the encrypted hash value in there too. The key that Alice will use to open up the, sorry, this was Alice's public key that goes in here. The key that Alice will open up this will be her private key. So she opens up and she's able to read the message now. So we have the message, and we also have the encrypted hash. Of the message. Okay, so she will take her own hash of that message, and then she'll use Bob's public key to be able to decrypt the hash of the message, and out will pop another hash value, and she compares the two hash values. If those values are the same, she knows that it was Bob's private key which signed the message, and everything will be okay. Okay, so that's the basics of using public key encryption to be able to encrypt and also authenticate. A key part here is that the public key that's sent over, public key such as this one here, will be sent as a digital certificate. So Alice's public key here is sent as a digital certificate to Bob, and then over here, when we're decrypting here, then again this will be a digital certificate which has Bob's public key on it. In the previous presentation, I outlined the PGP method. And with the PGP method, it differs in that we will get our message, we then take a hash of that message, and then Bob will sign that with his public key. And this is the key difference. Rather than using public key encryption, as we did here, we will use symmetric key encryption to encrypt the data. So now we'll generate a unique key, a symmetric key. And with this symmetric key, we will encrypt the message. Now what we do is that we take the symmetric key and we encrypt with Alice's public key. Okay, so here's Alice, and we've got Alice's private key and Alice's public key. So what will happen is that we'll take Alice's public key and we will encrypt that with her public key. And then we'll send the whole of the message and the encrypted hash to Alice. Alice then uses her private key to reveal the symmetric key. Then once she has the symmetric key, she'll be able to reveal the message and the encrypted hash. And then from there, she'll be able to use Bob's public key to prove the hash. So we can see that PGP differs from normal public encryption because we now use a symmetric key to encrypt the message rather than using Alice's public key to encrypt it. And public key encryption is okay for small messages, but it's not so good for large amounts of data, where symmetric key is much better for that. As a final little topic, we need to look at how we sign our messages. So I said it was an encrypted hash. It's not quite like that. We create a hash, a digital signature to sign for data. One of the most common is ECDSA, as used in Ethereum and Bitcoin. With this, as we saw before, we have Bob, and Bob will take a message and then we'll take a hash of the message, and then we also create a random value k to randomize the signature, and the output of this is a value R and S. And R and S are related to the signature so that Alice can also take a hash of the message she receives and checks it against R and S. Okay, if you want more details of how ECDSA work, then there are examples on the website. Okay, so we've investigated some of the key factors that we would have within authentication systems, and then on to some basic identity proving. Looked at the basics of public key encryption and how we can set up a digital certificate, some of the commands that we might use, what the PKI infrastructure looks like, and then how we can use encryption and also signing with pure public key encryption. But in many cases what we have is a symmetric key used for the encryption but public key used for the signing, and that was the example of PGP. Okay, thank you.